Hello everyone. Welcome to the 6G Symposium. This is the Air Interface panel. My name is Ernest Worthman and I will be the moderator for this panel. We have a great panel lined up with some of the most esteemed industry and academic speakers, starting with Emilio Calvinisi Strinati, who is the new 6G Initiative Program Director for CEA Leti. Following is Ray Dolan, CEO of Cohere Wireless. Following is Tom Marzetta, Distinguished Professor at NYU, and Charlie Zhang, a Senior Vice President of Samsung America. Welcome, gentlemen. So while there's a notable uptick of discussion in the 6G space, most of it is still in the labs, universities, and in the research segment. And since 5G is just at the starting gate, some questions if early discussions around 6G are warranted, even if it ends up being just what was left out of 5G, as some say it might be. The answer, of course, is yes. The pace of developing technology has quickened significantly since the turn of the century, so timelines are much shorter than for previous generations of wireless technologies, and parts of 6G will, of course, be integrated into 5G within just a few years. So 6G is certainly warranted in discussions today. It turns out there are really two parts of 6G, 6 gigahertz below and then 6 gigahertz above, aka the millimeter wave spectrum. We're going to do our best to address the air interface challenging in both. We will discuss topics relevant to the air interface, such as how we will accomplish getting 6G signals actually out there, both technically and logistically. Will this be a completely new transmission platform with new technologies, or just really the next iteration of 5G? What mechanisms will be involved? What are some of the technical challenges? And 6G and the millimeter wave spectrum are some of what we'll look at in the session. That being said, let's go ahead and get this party started. Tom, question for you to begin, start this all out is, what will be the enabling interface technologies for 6G?
So right now, if you look at what the researchers are doing, there are two things. Some researchers are looking at various extensions of MIMO and massive MIMO. Others are looking beyond millimeter wave to terahertz.
Interesting. How about Emilio? From the air interface perspective, will 6G define a new generation of transmission technologies, or simply just extend or modify existing transmission technologies?
Actually, we will have both of them. So it will be definitely the continuation. So actually, requirement will evolve from what we have in 5G, but definitely we'll need also revolution on, for example, on hardware technology to support the new exciting KPIs we have in 6G. For example, if you think about going to the sub-terahertz bands, things that are in discussion, let's say if you go to 140 and 200 gigahertz, and actually today there's not solid technology to provide all the hardware required for those. So the question here is actually if the hardware will be ready for the time, or if we have to look for other frequencies. So the debate is open and we are working that in research.
Okay, so I'm going to go with each of you and ask you one question, then we'll start some of the other discussions, and feel free, I will come back to you to add anything to the discussions you like. So Charlie, this one is for you. Tell me what the main driving use cases of 6G will be.
So it's still early days, Aaron, so I think a lot of good use cases are being discussed in the community. But we do see whenever we talk to our multimedia friends, everybody is getting excited about these new emerging, for example, immersive AR, VR, or XR, high fidelity mobile hologram. Really take you to realizing that vision, what we saw in those movies in Star Wars maybe 20 years ago, and digital replica. All these are really driving what we think could be very important technology advancement in 6G, because it requires much higher data rate, much larger capacity, and lower latency.
Tom, I saw you shaking your head. Would you like to jump in?
Agreed. I long have thought that AR, VR is the next big thing. I was predicting that 20 years ago at Bell Labs, it was considered too visionary at the time. But if you think about it, there hasn't been any new level of human-to-human communication in some time. The last one was when video was tacked on to audio cellular phone conversations, and that's approaching 10 years ago. The current 5G for the consumer on the street doesn't seem to have brought any perceptible changes. And I'm not saying, of course, that researchers and industry people are not coming up with interesting 5G applications, but they don't directly affect the man on the street. People are looking for the next level of human-to-human communication. And I think making it so that somebody 2,000 kilometers away can be right next to you in seemingly every respect is well worth going after, and will challenge researchers for the next 20 or 30 years.
Yeah, I've heard that. I like to call it XR for any reality that they come up with. And also 3D holograms are, you know, under the research microscope there too. Ray, I know you guys are looking at use cases for that. What is it that, would you like to chime in as well? You're on mute, Ray.
Sorry about that, Ern. Yeah, the troubles of these panels in this COVID era. So yeah, we do look forward to the world pioneering a new waveform opportunity. Tom's comment that the use case, the user on the street doesn't see much difference between 4G and 5G is because not a lot have changed between 4G and 5G with regard to the NR radio. So there'll be some change there, and we've been evangelizing OTFS for its merits. I'll save that for another forum, but that'll be one of the candidates that the world looks for. I think it's going to have the opportunity to go at very fast speeds, have extremely low latency. The other thing that I think is going to be a big part of 6G architecturally is to embrace the cloud. The only real access modality that has not embraced cloud and as a result doesn't have the economics of cloud is really wireless. And you see some of these cloud players getting involved, Amazon at Dish, AWS, Azure with AT&T and IBM with other players like Verizon. I expect the cloud players to have a lot to say about 6G architecturally. And you know, there's a tremendous amount of merit. If you start moving some of the intelligence to the cloud, you get a lot of system level benefits that right now only exist at the base station. So I'll just leave it at that high level as far as our view of 6G.
Thank you, Ray. If I have some time, or we have some time at the end of the session, we're going to talk a little bit about that OTFS. That's something I think people should know about. And now, Emilio, I'm going to you. I'm sure you see different use cases out there as well.
Right. First of all, right, to rebound what Tom was saying before, I do agree that we have been lacking for a new type of human-to-human type of communications. Actually, I would say the new challenge in 6G will be the real new human to artificial intelligence interaction and intertraining. And that actually will require a completely different approach, which we're not just delivering bits in a reliable way from one part to another, symbols, but delivering meaning and transferring knowledge. And actually will require a lot of changes. And on this kind of thing, we're starting for 6G, and that definitely will open different type of services and use cases where actually you will have real interactive relation or interactive communication, not only with real people, but also with this, I would say, artificial intelligence will provide you a new type of experience.
You know, I just got a question in that I think is extremely pertinent and something that I've actually been very interested in myself. It says, what are the chances of intelligent reflecting surfaces be included as part of 5G? I'm saying it's going to be all of that, but you guys want to comment on that? Start with you. Start with you, Emilio. Yeah. Go ahead.
Okay, so I have the honor to be the coordinator of a big project in Europe named RISE 6G, which actually is devoted really on the studies of these recurrent probability intelligence surfaces. So from some point, it might be either something that we'll have at the end of 5G, because from an architectural point of view of 5G, it's possible to include that. From the technology point of view, it really depends on which frequency you're working with. So if you work at low frequency, I would say the recurrent probability intelligence surfaces are really a reality today. So it's something that can be ready in a few years to be trial and then to be integrated. Then if you work for subterranean communication or millimeter wave communication, then you have a lot of technology issues, which it might be that you can include that in the network, but still the energy efficiency of the surface might be something, let's say, controversial. So from a point of view, recurrent intelligence interface is definitely one important point for 6G. It will be one pillar. It might be either the some easy and developed mode of this use of this recurrent intelligence interface will be already at the last end of 5G.
Interesting. Charlie, want to chime in?
Yeah, sure. Definitely, this intelligent surface is very important area. I think a lot of interest on that. So probably there's two aspects. I heard that the question is specifically on 5G. Maybe he meant for 6G as well. So from that perspective, I think maybe technology anyway, the advancement will be continuous. But if you look at timeline for 5G or 6G, right now we are still in release 7. If you look at 3GPP discussions, release 18 was supposed to start next year. So I think most of the companies or people in the community think that maybe 5G or 5G Advanced will go a couple more releases, for example, to release 19 or 20. So that's when we'll start gradually transitioning to sort of early 6G requirements and use case discussion, later followed by technology discussions. So that's kind of where we are. So definitely that's just timeline. From a technology perspective, also typically the way in industry we handle things when a new technology shows up is to look at its merit and then probably figure out a specific use case. For example, is it good for urban scenario? Is it good for rural scenario? Or is it good for both? Then do a thorough evaluation on each and every one of those use cases, and then decide whether to include them in one of the releases. So probably do the same thing for that as well.
Tom and Ray, I'll get to you in a second. Ray, I want to ask you a question, though. I know that Cohere and its OTFS technologies are pretty unique. I'll bet that has a pretty good link to radiating surface antennas type of technologies.
Yeah, it's interesting, Ern, not just the way you radiate from your own antenna, but ironically, this is the way I look at it, and this might be a little bit simplistic. We're already in the presence of intelligent radiating surfaces, but we actually don't see them intelligently because we're looking through time frequency, and through time frequency, they're coming in superimposed, out of phase, and with a delay spread, and they look destructive. But ironically, when you move from time frequency to delay Doppler, which is the derivative of each case, delta time and delta frequency, they actually expose themselves as individual reflections. And it's amazing. They're highly trackable across time and frequency. And you can actually code on the individual reflections. So what I'm saying to you is, I know this sounds a little bit, far-fetched, but your question actually triggered me to think about it that way. In a world of intelligent reflections, we're already there. It's just that they're coming in to the receiver in a way that are destructive, and we try to equalize them out. But if you see them individually, they actually each become an additive component to the energy. So that's what we've been able to do with delay Doppler, because OTFS is really our waveform, but with the delay Doppler mathematical domain, which is where Cohere really experimented, the individual reflections, and there can be up to 15 dominant ones, each expose themselves, and then they become highly predictable for a couple of hundred milliseconds and highly predictable for several hundred megahertz. This is why all of a sudden reflections become your friend. It's like when Qualcomm said a second finger during a handoff becomes your friend, and it didn't make sense to me, being an FDMA, TDMA guy, until I realized that they were creating a coherent handoff. We're creating a coherent set of beams. And it's a really interesting space that I think just opens up an entire Pandora's box for architecture. Sorry to hog the panel. Back to you.
No worries. Okay, Tom, you're on.
I think it's important with respect to intelligent reflecting surfaces to distinguish between what fundamentally this technology offers and what does it offer in terms of cost effectiveness. Fundamentally, anything an intelligent reflecting surface can do, phased array can do also. So it really boils down to, is this an economical solution? It seems self-evident that it could be a great enabler for terahertz, where just in order to maintain the power aperture product, you're forced to use numerically huge phased arrays or some mechanically steerable dishes or something of that ilk.
Okay. Anybody else got a comment or two on that? Okay. Let's me bring my notes back in, and let's move on to the next one. Give me 1 second. There it is. So one of the questions that everybody's lips, I shouldn't say it's a question, but one of the platforms has to do with artificial intelligence and subsets of machine learning, machine intelligence. I think this is something that all of you would be very appropriately versed on. So I'm going to start and go around and say, okay, let's talk about this for a minute. Tom, I'm going to start with you.
Not an expert at all in AI or machine learning. Certainly for higher layers of the wireless stack, that offers considerable promise. You have traveling salesmen, difficulty sorts of problems, allocating resources. If there are strong nonlinearities in the system, I don't think that our mathematical tools are particularly sharp. So quite possibly AI will help out there. But in terms of really inventing something fundamental at the physical layer, I believe until we can build an AI machine that knows Maxwell's equations and is cognizant of Shannon's theorems, I don't think that the AI machine learning is going to give you breakthroughs there.
That's a really interesting perspective. I haven't heard that one. I appreciate it. Charlie, you're shaking your head. Come on in.
Well, I definitely understand where Tom is coming from. I think it's also up to all the community to really stand up to that challenge, show us where the AI is really meaningful. But from what we are seeing, AI is already making a difference. Not even for 6G, but even when we're talking about 4G and 5G, we see a lot of good application for AI today. Both from the network side as well as from smartphone device side. On network side, we see a lot of good applications, especially in areas traditionally, it's a lot of these very labor-intensive, maybe repetitive work that can be done much better, easier, cheaper with AI. For example, automation, orchestration, management, network management, root cause analysis, anomaly detection. A lot of these things, we see a lot of good application that's already happening today, making lives of our engineer a little bit better. Now, the question is probably, given that we already have 4G and 5G, looking forward to 6G, what could be different? How can AI be a fundamental part of 6G design? So that's where probably the question is. We do see that there's some chance, some hope, so to speak, that we can design AI in a more native way in the future interface, as opposed to what we are doing today. Today, because 4G, 5G, the protocol, the standard is already there. We are adding AI layer on top of what we already have. So going forward, I think, how did you design this? How did you identify areas where AI native design can inherently be better, more optimized than the traditional protocol design? That's a big question. We do see that there's some hope for that.
Emilio, what do you think?
Yeah, first of all, I'd like to wonder where innovation is. So if you look for what we have in 5G, at the end, 5G is actually an excellent platform to collect big data and actually feed AI with a lot of training data for optimizing all these algorithms. At the same time, AI is actually optimizing roughly everything. That's the promise. But this is actually not the field of innovation of 5G. It's the way we use AI. Actually, what will be, from a point of view, the innovation 6G on AI is actually the way we'll use the network for inter-train intelligence again. So actually how we actually take into account the logic the different agents use in order to choose something, and indeed how you decide what is meaningful, which kind of knowledge you have to transfer from one point to another of the network. And actually, that's from a point of view, the core innovation that 6G will bring to AI.
Thank you, Emilio. Ray, you get to talk too.
Hey, thanks. I want to gently push back on something that Tom said, and this is why. I get the notion that Maxwell's equations and Shannon theory has led to this notion that the black box of wireless is what it is, and it appears to be random, and as a result, how can AI ever catch up to that? But what we're finding in the delayed Doppler domain is that, in fact, there are massive patterns in the reflections, And just because they come in randomly in the aggregate, individually, they can actually be predicted. So we're actually using AI right now to look for those patterns. And there's tremendous promise in the notion of beamforming with AI. The other thing I just want to point out is that this is going to drive a pretty good architectural discussion about whether you should bring AI out to the edge, where the edge is a base station in today's world, or whether you can bring the intelligence to the edge when the edge is actually the edge of the cloud, which is a data center. And since everybody's worried about latency, the perception right now is bring the intelligence to the base station, you can't add any latency, and it's already massively complicated. What we're finding, though, actually, is that we have a coherence time of 200 milliseconds, and we actually can re-architect things. And so this whole notion of AI, Ern, is a huge field that we're planning to pioneer in combination with the cloud players. The AWSs, the Amazons of the world, the IBMs of the world are absolutely interested in re-architecting the wireless network.
Interesting. One of the interesting questions is, when you work at higher frequencies, we're talking now hundreds of gigahertz, the millimeter wave end. So, you know, the higher we go, we all know what the propagation issues between high frequency are. So how do you get reliability and what I like to call bulletproofing so that the actual applications will be reliable enough that the user won't go, this is not worth it, and walk away? Talk a little bit about that for me. And Ray, I'll start with you.
So as I understand your question, how are we going to get reliability, period? And it's going to get even harder when you go to higher frequencies. That's at least how I think of the problem, Ern, if you don't mind.
I agree.
I think you got to know the SNR before you fire the bullet, right? And this is, again, one of the artifacts of going into the delay Doppler model and creating this notion of a predictable channel, is that we actually have the channel state before we fire the gun, right? So before you even code the channel, you know what the target block error rate is, and you can get to a better outcome with this architecture. Now, at higher frequencies, I'd have to think about it. I'd probably defer to the folks that have more scientific background on frequency itself, but I don't think the problem gets any harder than just having smaller base stations and smaller base stations and smaller base stations. Now, I may misunderstand that. I'll defer to my other panelists on why reliability is a function of frequency. But my point of view is it's more reliability, if we're really going to solve it, is when we can establish a priori knowledge of the signal to noise ratio, code accordingly, and guarantee the experience. And that's a path we're pioneering right now at Cohere.
Nice. Tom, I'm going to let you come in on this one, then Charlie, I'll get to you.
So your question is how to achieve reliability at terahertz, but is reliability now guaranteed at millimeter wave? I'm going to pose it to the rest of the panel, the question of to what extent has the blockage problem been solved? I mean, the perennial solution offered is more and more small cells, and then be connected simultaneously with several of these, which of course reduces your overall spectral efficiency by a factor of 3 if you make it threefold. Professor Shiv Panwar in NYU Wireless has done some research with his students establishing that yes, if you're hooked up to several base stations at one time, outages due to blockage are less frequent, but when they occur, they last just as long as before. And so
Charlie, come on in.
Oh, yeah, sure. So I guess the challenge and opportunity always goes together in some sense. And being engineers, we all love these technical challenges for Tom. So I do agree there's a lot of challenges. I mean, starting from millimeter wave, and especially now we are talking about going even higher in terahertz. But probably we need to take a step back and think about why we are looking at these frequencies, at these spectrums. Part of the reason is they are out there. There's abundance of these spectrums out there, especially if you talk about above 100 gigahertz and all the way to 300 gigahertz. I mean, that's 200 gigahertz of good spectrum. That's multiple times what we have if you add up all the spectrum we have been using from 1G to 5G. That's a fundamental reason. That's why it's attractive to think about these new spectrum bands, because when we talk about XR, when we talk about hologram earlier, right? So you need some carrier, some wireless spectrum to make that a reality. And also when you go higher in frequency, it also helps you realize some of the vision, for example, communication and sensing convergence going forward, because going higher in frequency makes the wavelength a little bit smaller. You know, if you build a array in your smart devices, you can do much better, much higher resolution sensing for the environment around you. So that's part of the reason we are going there. Now, of course, I mean, as you said, there's a lot of challenges. I mean, the path loss is just one of them. There's multiple others, including how did you make your PA efficient and pump out enough power? How did you make your LNA more efficient? And recently, as we look into some of these above 100 gigahertz spectrum, we realize there's new challenges that we never experienced before, including on the how do you package semiconductor? I mean, in the past, we are so used that antenna is much bigger than chips we play with. But now, once you talk about 150 gigahertz, we are talking about a wavelength that's 2 millimeter. So traditionally, if you use half wavelength antenna array, that means between two antennas, you have only 1 millimeter for you to play with your chip technology, place your chip and package it. So these are really unprecedented challenges. So, but we are pretty confident as a community come in and see the value of this new spectrum, start to invest in R&D, we will eventually be able to overcome these challenges.
Very well. Emilio?
Yes, so I completely agree with the other colleagues in the panel that first of all, blocking is still a huge problem. Either if you can reduce the probability that happen when happen, actually the link is broken somehow. But the second part is also in case of mobility, still we have a lot of problems. This high frequency of this very narrow pencil beams that actually you have to align, and actually because of mobility that's come to be a very big problem. And the third part is also in terms of energy consumption, it's actually still a very huge problem. Just to give you an example, if you migrate from 5 gigahertz to 28 gigahertz, you have roughly a factor of 1,000 losses in the coupling of the antenna module and the RF module. And actually, you need new types of hybridization materials for which you co-design the RF and antennas, for example. So there's a lot of technology there that somehow is not effective enough today to provide a good efficiency in terms of energy. So there's a lot of work from point of view, not only on the system level point of view and architecture, but really on what the new hardware, new technology can play to make an effective reality, and not just using the service for 2 minutes, but maybe stay there for hours and hours with your battery still there.
Interesting. So let's take a sidestep here a little bit. One of the things that is coming on with 5G, and certainly will be a big player in 6G, has to do with these new platforms or these new demands of ultra low latency, extremely wide bandwidth. Where do you see that coming from in 6G, and how do you see it applied to, let's talk about some of the higher frequencies above 1 gigahertz? And I mean, if you want to talk about it below 6, that's true. I mean, that's good as well. But if you want, I'm kind of interested in where that would go in the millimeter wave arena. Tom, you want to start out?
Rephrase or expand on your question a little bit, please, Aaron.
So, one of the things that we've been talking about, and it's been a real, sweet spot with everybody, are things like ultra low latency. Who's going to be needing ultra low latency? Who's going to be needing extremely wide bandwidth? Who's going to be needing nothing at all, or just typical, perhaps, industrial type applications? So how are we going to, at 6G, and especially, like I said, at millimeter waves, make ultra low reliability URLLC and be able to use 100, 200, 300 megahertz bandwidths for high demand applications like multimedia or massive communications, MMT, massive machine type communications? How are we going to make that work in 6G versus how are we making it work in 5G?
Okay, I won't attempt to answer comprehensively your question. Let me just say a little bit about the latency, and let's be a little more specific. Some people, for instance, are looking at closed loop control of drones using 5G. To my mind, Yes, of course, they're thinking conventionally and they're going to get some success. But why should you ever digitize and code these signals? I mean, if you consider you have actuators on the robot or on the drone, and you have sensors, you're sending this via wireless to some sort of controller, it's making decisions, sending command signals back to actuators. Who says you should do channel coding, error correction coding? Why should you ever maybe you shouldn't even digitize the signals. So if you want to reduce latency, get rid of all that nonsense and do it much more directly. Treat it as an old-fashioned closed loop control system, and the best you possibly can do is probably stay analog.
That's an interesting answer. Very interesting. Ray, what do you have to say?
Well, I'm going to have to process that answer. That was quite an interesting answer. It makes my head really think differently, Tom. So thanks for that. So I guess, Ern, I'm trying to just boil this down to maybe 2 points. One, I think we're going to need a hybrid control plane. A portion of the spectrum is going to have to be able to be managed from the cloud, and a portion of the spectrum is going to have to be overridden by cell site decisions that are made at ultra low latency requirements. So I think first, the brains of the system are going to move to a distributed architecture, much like a microservices architecture in the cloud, where the cell site can take a portion of the spectrum that really requires ultra low latency and ignore the commands from the cloud, but otherwise the majority is going to move to the cloud. So first answer would be hybrid control. The second thing is, I think we're going to have this a priori knowledge of the SNR, so that when someone raises their hand and says, I want to speak, you already know their channel. You already know their SNR. You already know what you need to encode it with, even though now I'm going to have to think about not encoding it at all, just putting it in analog as Tom's talking about, which makes a ton of sense. So I think it's this a priori knowledge of SNR, so that the transport layer is ready to go before the access is even required. And then a hybrid control plane. I'll pass it back to you.
That's an interesting angle to come from. Emilio, what do you have to say?
Honestly, I don't see much to add to what Ray said. I completely agree that this going to analog is something we are exploring in my group. Actually, it's something that it's very promising. So I support this idea. We can continue discussing about that. Definitely, it's a good lead to do at least part of the communication part. Of course, not all, but I mean, yes.
Charlie, what do you say?
Well, if you look at how the 5G adoption is taking place today, so it is true, maybe the early adoptions, but by the way, it's really fast pickup. As of second quarter, we already have around 400 million users worldwide using 5G service. But vast majority of that is probably still belonging to what we call EMBB, Enhanced Mobile Broadband category. But we do see promising signs that URLLC type of application is picking up pretty rapidly. A lot of investment, a lot of interest. You know, for example, the industry automation, remote sort of medical education. Even some people are experimenting with remote surgery, which all requires a lot higher requirement for these latency, how much you can tolerate. I mean, that's very promising. I mean, again, we have to understand whenever we have a new generation, it takes time for different types of applications to materialize and mature. So not every application may happen at the same time. I mean, in terms of technology, I think in the 5G, the air interface delay was reduced, from somewhere around 10 milliseconds of 4G to 1 millisecond of 5G. I would say a big part of that is because of larger bandwidth that's being used in 5G. We were able to support 100 megahertz carrier, individual carrier in 5G as opposed to 20 megahertz in 4G, for example. So that's a big part because you're sampling faster. By nature of it, your latency is lower. But there's also a set of other tools that's being built in 5G to support URLLC type of traffic. I think it's also very useful. Now, of course, this will go on naturally in 6G. If we talk about higher frequency, if we talk about exploring new bands between 100 gigahertz to 300 gigahertz, the amount of bandwidth we are we can afford will be even larger. For example, we can afford maybe individual carrier to be 2 gigahertz, which is about 20 times faster compared to what we had in 5G. So that by itself can give you 20 times less latency. As easy as that. Of course, there will be other tools that will naturally eventually built into the system to make it work better and better control. Because in order for low latency system to work, it's not only about numerology, it's also about all the control channels, and data channel has to work together to close the loop. But I do see this is happening, and it's maybe it's not as fast as adoption of eMBB, but eventually I think this will happen.
Very good. Let's step off a little bit into the real world of hardware and software. Tell me what you think the new hardware and software platforms and technologies will look like when we talk about 6G, and particularly as we go up higher in frequencies. We can, like I said, we're talking about up to 300 gig right now for the most part. I wouldn't mind you talking a little bit about what we might start looking to see in terahertz at some point. Emilio, let's start with you. You're on mute. There you go.
Yes, I'm here. Okay, so typical problem. So that's a very good question. Actually, it's an open question whether we are considering which kind of technology can be used on this kind of frequencies. Because the point is that if you look for silicium technology, we can say we are good up to 130, 160 gigahertz. And then actually start the point that we see limitation, especially in feeding the output power needed for the type of application we are considering. And actually we have a real depth value between 130, 160 gigahertz and 20 gigahertz, for which we have some few processing technology where can, accomplish the goal, but with a very horrible energy efficiency at the moment. So if we want to merge a thing, we have to be energy efficient, and we want to also hybridize using hybrid materials to also stack antennas on ref components and so on. At the end, I would say that honestly, there's a very huge open question about how to do if you want to go beyond 130 gigahertz. So the moment it's really open research in terms of which technology can be used. You are mute now.
Oh, that was good. Tom, what do you see happening, at 300 gigahertz for hardware and software?
I think Ray and Charlie can answer that question better, but I don't see there's any reason why the system should resemble what we're doing at 3 gigahertz. If spectrum is so cheap or ubiquitous and plentiful that it isn't worth metering, then you're never going to want to do spatial multiplexing until, of course, you finally run out of terahertz spectrum. Instead, you're going to want to give each user her or his own dedicated spectrum. And you're not going to want to do anything complicated. You're going to want to give them as much bandwidth as possible until the SNR in each received frequency band is about 0 dB, which represents the sweet spot. In short, you're going to do the simplest possible things. And not to be a broken record, maybe even some old-fashioned analog schemes are worth looking at again. Wideband FM is exceedingly good. It produces a constant modulus signal, which RF amplifier designers love so much. For the first time, we have enough bandwidth so you could actually put an old-fashioned black and white TV signal in wideband FM. It's never been done before, as far as I know.
Yeah, you and I are old schoolers when it comes to analog, aren't we? Ray, what do you have to say?
Charlie, it reminds me in The Wizard of Oz when Dorothy said there's no place like home, and if I can't find it in my own backyard, it doesn't matter. I don't think we're going to go up the frequency band. I'll let Charlie answer the question if we do, what the hardware looks like, because honestly, we don't have a dog in that fight. Our goal is to let the folks make more use of the existing spectrum. We're doing experiments. We're doing actual trials, commercial trials with operators. I won't name names. We're doing it at 600 megahertz, 800 megahertz, 1.9, Turns out that FDD works with MU-MIMO. So I believe the industry is going to spend another 10, 20 years in the existing frequencies. And during that time, we'll break through the physics issues and the hardware issues on some of these higher frequency bands. That's my take.
I won't have to worry about that. Charlie, what do you have to say?
If you think about terahertz or maybe higher frequency, naturally, I see that two things will happen. One is the base station will look smaller, right? Just by the nature that you're going higher in frequency, everything, antenna, as I talked about, packaging, this chip size will become smaller. So as an end result, the base station that you have will be smaller. The second thing is you're going to see more of that. That's because the path loss will be higher in those frequencies. So naturally, we have to consider new type of topology, how we build a network that's more robust and resilient, can reach people. What if one link gets blocked, as Tom mentioned earlier? How did other link come in to help out with the communication need? So, but the good thing is because the size of these future devices will be smaller, it might be easier for them to be deployed. The requirement on the power, real estate on top of the cell tower will be less strict compared to what we are seeing today, hopefully.
Okay. I'm going to put Tom, please go ahead.
Just a little bit of a point of issue with Charlie's comments. I don't think the fundamental path loss is any greater at terahertz than it is at 50 gigahertz. It's still power falls off as 1 over r squared. The issue is that if I am using near omnidirectional antennas in my handset, I have to maintain the same total radiating area back at the base station. And so I don't see how these base stations are getting smaller. And of course, this because this is now so many wavelengths across, a factor of 100 in each direction with respect to 3 gigahertz, it means you need 10,000 times as many antenna elements to fill this big aperture.
Okay, let me respond to that.
Problems with terahertz that I see.
Yeah. Go ahead, Charlie.
Yeah, Tom, great point. Indeed, if you are able to keep the antenna aperture the same as, for example, 3 gigahertz, definitely you can reach the same distance as you're saying. But then you run into practical challenges. I mean, can you really put 1 million antennas there? Can you really put 1 million RFICs there and keep them phase coherent and each of them pumping out enough power to go that distance? I think we are talking about initially, at least, the practical, feasible sort of the base station size will be much smaller than what you're seeing in 3 gigahertz, and therefore it will reach less distance.
Yeah, the age-old question: can we do it in theory? Of course. Can we do it in practical? Maybe. Emilio, do you have anything to add to that discussion?
Oh, that's fine. Yeah.
Okay, Ray? Okay, so we're got maybe 10 minutes left in this, 12 minutes. Let's talk a little bit about on the semiconductor side, and there we go to the practical end of things, as you talked about, Charlie. We've kind of run up against a couple of walls in the semiconductor manufacturing because the wavelengths are getting so small and the gate distances are getting so small. If we get up above, let's say if we get into terahertz, how do you see semiconductor technologies evolving to meet the ability to develop a device that's capable of radiating a terahertz or 900 megahertz, 8 or 7 or 600 megahertz? And Tom, I'm going to go back to you first.
Sorry, not my field at all, but I remember some years ago, optical people at Bell Labs, and by the way, these optical physicists were incredibly smart. Every year, a new earth-shaking record in optical fiber transmission. I always thought we would really make progress if we could just make wireless people out of them. But they used to talk about direct generation of RF by, of course, heterodyning 2 lasers at different wavelengths together. I'm not going to say anything more.
Okay, thank you, Tom. Emilio?
Yes, actually, there are a lot of technology we are consuming at the moment. First of all, there are technologies based on CMOS. And then we have also incision germanium, the GaN and IMP The point is that the scaling of the CMOS doesn't go as fast as we want with the frequency we want to adopt to 2030. So at the moment, as I said before, also in my comment before, there's a thing that we can achieve, let's say, we can deliver the output power to this, but we cannot achieve a very good energy efficiency. What I'm not saying, when I say energy efficiency is not good, I'm speaking about either 2-3% is not possible at the moment. So at the end, the point is that we can go for this communication on high spectrum, but we can really do not reach with the technology we have today, with the vision we have today, the good performance we need for sustainable communication. So it's really hot topic of research, and I guess most of us has not at least not secret answer to that.
Ray, anything to add?
Well, Ern, respectfully, I got to push back on the question, and this is why. It's the notion is it's a foregone conclusion that we're going to go up to these high frequencies. So how are we going to solve it? I take us all the way back and say, what the hell are we doing wandering from the frequency we're at? Okay. The bottom line is the frequency we're at works well. We got a little bit head faked by saying you can't do this on paired spectrum. So since 5G was all about the MIMO buzz, you had to go to TDD. Once you had to go to TDD, you had to go to something new. And once you go to something new, why don't you just wander all the way out into space, right? But if you come all the way back home and you realize that you can do all of this stuff on paired or unpaired spectrum, we're working with operators that are saying, upgrade my 4G networks, upgrade my 800 megahertz network. So I don't have, first of all, it's kind of nice that I don't have a good answer for you anyway, so I'm changing your question, right? I'm not a physics guy. I'm not a silicon guy. I defer to Charlie and others on the panel all day long. But I actually think the flaw is that it presumes that we're all going to go to terahertz spectrum, when in fact, we're going to be able to create 100 times the capacity in existing networks if we just refarm them using the fundamental tools of cloud and the fundamental tools of MIMO.
So I'm going to say you're throwing 6G out the window. We're never going to have it, right?
Just 6G is going to absolutely solve some of the architectural issues. See, this goes back to, if you remember, there was a time where we were going to have a wireless web, because right. You see, the web doesn't work in wireless, you see, because wireless is just special because it makes mistakes and it can't keep up with the latency requirements of TCP/IP. So we were crazy enough as a company to try to solve that, because we thought the web was here to stay. And we thought there would be one web. And of course, now it's obvious. But there were panels like this that said, what are you going to do with this entire parallel universe called the wireless web, where you did ringtones and other things. And the world's going to come back to existing spectrum on TDD and FDD, sub-6, my opinion, for another 20 years, while it explores higher frequencies. And 6G is going to map the things that 5G didn't do. It didn't create a new waveform, and it didn't embrace the cloud. And those are the two motherlode things that need to be done in 6G. Frequency, my opinion, is a sideshow.
We'll talk about this in 2032, you and I.
You got it.
Right, we're down to our last 10 or 9 minutes, and I've got some questions I'd like to throw out at you, if you don't mind. I've got one for you, Tom. The viewer says, which approach do you think will eventually be the winner for 6G? Keep trying to improve spectral efficiency in the current spectrum below gigahertz through massive MIMO, or instead going for wider bandwidth in sub-terahertz? Or maybe in the end it will be both. Actually, Ray did a good job of just answering that one, but if you have something to add, Tom, it was directed at you, please.
Well, this huge spectrum at millimeter wave and terahertz is available. We've got to learn to use it, so I'm all for allocating resources. But the latest auctions for millimeter wave spectrum, 10 times the carrier frequency of the midband stuff, but selling at 1%. So the midband spectrum is selling for about $400 per hertz. That was an FCC auction within the last year and a half. Millimeter wave, $2 per hertz. And so it's, I agree with Ray that if you're a smart inventor, the greatest potential for payoff is in the mid-band below 6 gigahertz. The other thing is, just pitching in a personal thing, my group is doing what I call physics-based wireless research. The idea is bring the basic wave propagation physics much closer to the communication theory. So in 1943, Sergei Shelkonov at Bell Labs discovered superdirectivity, which has been exploited on a very minor level, but nobody has figured out how to scale it up to the level we would like it to be. So this is still another way of getting 100,000 times our current spectral efficiencies.
Anybody else want to chime in for a quick word?
Hey, this is Charlie. Maybe I can just quickly add. So definitely, in my view, both paths we should explore. I mean, even if you look at what happened in 5G, a lot of people talk about millimeter wave, but what's being less talked about is a lot of innovation happening in below 6 gigahertz as well. So, for example, the massive MIMO technology, which started in 4G, gets really optimized and become a mainstay in 5G. So very much, I think the same thing will happen. We're going to look at the spectrum that we're already using today. There's no doubt about that. We're going to look at below 6 gigahertz. We're going to look at millimeter wave. In the meantime, we're going to look at these new spectrum. So I really hope some of the things, for example, Tom was talking about, this physics-based MIMO will become very useful and give us yet one more tool going forward to achieve this capacity and throughput. I mean, I just want to remind everybody, part of the reason we are starting this year, 2021, talking about 6G, which most people expect will happen around 2030, is it takes time. It takes time to create these technology reserves. It takes time to invest and really build the ecosystem. That's why we are doing it so early. So lessons we learned from the 5G days, you've got to do it early. So the debate of which one is better, I think let's wait. Naturally, let the market decide. But for now, R&D, I think we need to really get together and focus on investing.
Thank you, Charlie. One more question. We talked about this a little while ago about the different URLLs and EMBB and all that, but one of the questions is those three things, EMBB, MMTC, and URLLC, have been very prominent in 5G. Will they be as prominent in 6G as drivers, or will there be something different that may pop up? And again, as we go down the road a little bit, we know below 6 gigahertz this is going to play heavily, but what about down the road somewhere? Are there going to be new things we don't know about pop up that may be in the crystal ball? Tom, let's start with you.
I'll pass on that one.
Okay. Ray?
So, Ern, my view, being in this industry for a while, is wireless is just what allows you to move and do things you do on a wire. So I think the innovations that are coming in the wired world, our challenge is just going to make them work in the wireless world, as opposed to creating something that's unique to wireless. Now, autonomous vehicles and things like that might be unique to wireless. So there's your cat. You did predict that, by the way. So great job. So I actually think the machine-to-machine stuff and the AR and VR stuff is going to be huge. Let me just leave it at that and pass it on to some of my other panelists.
Okay. Emilio, your answer?
Okay, so if I will understand indeed, the question is which will be the new services? Because the other one we already have it. I guess first of all, there's one breakthrough will be the inclusion of non-terrestrial networks. So this 3D dimension of those. So actually will be services that will be delivered also not only on the ground. And second part, that actually there's a lot of thinking about holographic communication, interactive 5 sense communications, intertraining of AI intelligence. So again, this will be an umbrella for new types of semantic services in which what will be important is the meaning which is conveyed in the communication, and that change everything. So you can really have new types of service in which you interact with something far from you in a deeper way, in a more immersive way.
I'm sorry. Thank you, Emilio. Charlie, your turn. That's two. I don't get three. Charlie, are you there?
Oh, sorry.
I'm sorry,
Yeah,
I missed.
I
Yeah,
can
your
hear
turn.
you. So yeah, definitely, I think Emilio has a good point. NTN and this new topology will be very interesting to look forward to down the road. And also, I look to probably would like to add on top of a comment maybe Ray made a little bit earlier. He was really thinking about the role of wireless industry as a whole. Wireless is mostly understood as a communication, right? We are here to ferry packets from point A to point B. So from that angle, I do see some exciting movement going on, especially with possibility of more AI native design going forward. I do see the convergence between communication and computing down the road in the 6G days. I mean, for example, today, I think the service, people understand, you go to a cloud, you stream a video, that's consuming some of this content on computing, but it's being ferried from those cloud servers to the local devices. But down the road, I think we can imagine a future where computing is sort of natively buried as a fabric of communication network as well. So, not only do we provide these services for communication, ferrying bits and packets, but also providing service in an integral way. So that will be very interesting to see if it becomes a reality in 6G.
Okay, gentlemen, we're down to our last 2 minutes. Each of you have about 15 seconds to impart your last, most thoughtful insight. Tom, starting with you, and I'll shut you off at 15.
Fair enough. I think that no existing wireless system is operating anywhere near limits imposed by nature, but we really need to do much more fundamental research if we're going to close the gap in performance.
All right, Emilio? You're on mute.
Yes. I would say now is the crazy part of the life where actually you can work on 6G in almost unconstrained research. You can really dig on something you believe can be worth and see if it can happen. So concentrate on that and not just think about what is 5G, what might be 6G and so on. Find the lead and go ahead.
Thank you very much. Ray?
Thanks, Ern. It's time to shatter the notion that wireless is a fast fading channel and non-deterministic and can't be characterized and predicted. In fact, the wireless channel is nothing more than up to 15 reflectors that are completely deterministic. They move very slowly relative to the speed of light, and they can be predicted across both time and frequency. It's the interaction of the modulation scheme with the channel that creates this notion of fading. And once you stop chasing that, it's like the snow globe that you put on a shelf. It settles down and life gets really simple. That's the world of delayed Doppler. We look forward to sharing it with you. Back to you.
Gentlemen, we are out of time. It has been such a pleasure chatting with you. I'm so glad we had to do this, and we're going to shut her down. You guys have a great day, and I hope to talk to you guys again soon in the future.
Thanks.
Take care, everyone.
Thanks, Ern. Take care.
Bye-bye.
Thank you.
Bye-bye.
Bye.